Hello everyone, I'm Wang Yanhao from the University of Helsinki. Today I will present our work, Minimum Coresets for Maxima Representation of Multidimensional Data. First of all, I will introduce the background on coresets, a method for data summarization via geometric approximation. A coreset is a small subset that can be used as the proxy for the full dataset. For a given class of problems, the solution obtained from the coreset can approximate the solution obtained from the full dataset with theoretical guarantees. Coresets are useful in many approximation domains, which are listed as follows. In this work, we study the problem of coresets for Maxima representation. For a point set P and the class F of all linear functions, the Maxima representation of P is the subset of P containing the maximum of every function in F. Here, we consider the set of all linear functions, which is defined by the inner product between the vectors and the points. The exact Maxima representation is the set of vertices of the convex hull of P, or equivalently, the set of extreme points. However, the exact Maxima representation may still contain a large number of points, particularly so for higher dimensions. So we further introduce the coreset for Maxima representation to reduce its size while preserving the theoretical guarantee. We formally define the epsilon coreset for Maxima representation. A subset Q of P is an epsilon coreset for the Maxima representation of P if and only if it achieves an epsilon approximation to the maximum of P for any vector in d-dimensional Euclidean space. One notion closely related to epsilon coreset for Maxima representation is epsilon kernel in computational geometry. The main difference is that epsilon coreset is defined on one-directional wise, but epsilon kernel is defined on two-directional wise. However, both notations are still closely related to each other, which is given by the results here. From the algorithmic perspective, any algorithm for epsilon kernel computation can also be used for epsilon coreset computation. And from the application perspective, both geometric optimization problems and database applications that are effective and epsilon kernel approximation can also be approximated by epsilon coresets. In all these applications, smaller coresets are preferable to larger ones because of higher efficiency in optimization and more compact data representation. Therefore, we aim to find the epsilon coresets of the smallest size, which is defined by the minimum epsilon coreset problem. Given a set P of points in d-dimensional Euclidean space and an error parameter epsilon, the minimum epsilon coreset problem aims to find the smallest epsilon coreset for the Maxima representation of P. The minimum epsilon coreset problem, or MC for short, is closely related to the regulator minimizing set, or RMS problem. The RMS problem is proposed for representative skyline selection. It aims to find the smallest subset whose regulator ratio is at most epsilon. Here, the notion of regulator ratio is equal to the notion of loss in maximum in the MC problem. The difference between them is that the RMS problems is defined on non-negative points and vectors, but the MC problem is defined for all possible points and vectors. From the algorithmic perspective, most algorithms for RMS cannot be applied to MC, since they are based on the non-negativity of points and vectors for solution computation. However, the algorithms based on transforming the RMS problem to a set cover problem can be simply adapted to MC, as shown in the SCMC algorithm later. We prove that the MC problem is NP-hard in 3 and higher dimensions. The key idea of the proof is to reduce from an IMS instance to an MC instance. We first propose an optimal algorithm for MC in 2 dimensions. The basic idea of our 2-dimensional algorithm is to solve the MC problem as an archiving problem based on the geometric interpretation of MC. Here, the archiving problem in 1 dimension is not NP-hard, so we can transform it into a shortest circle problem in a directed graph and solve it optimally. Here we simply introduce the 3 main steps of our optimal algorithm in 2 dimensions, which are candidate selection, graph construction, and solution computation. Here we list some theoretical results for our optimal algorithm in 2 dimensions. The MC problem becomes much more challenging in 3 and higher dimensions because of the NP-hardness and the inefficiency of computation. So the basic idea is to transform MC into simpler cover problems. We propose 2 efficient approximation algorithms for the MC problem in this paper. The first algorithm, DSMC, transforms from MC to dominating set problem in a directed graph, and the second algorithm, SCMC, transforms from MC to the set cover problem. Next, I will introduce the DSMC algorithm for the MC problem. The motivation of the DSMC algorithm is that the convex hull is the minimum 0 coset, and for some epsilon greater than 0, we can remove redundant points from the convex hull, such that the remaining points forms a valid epsilon coset. The reduction procedure involves the inner product Dionis graph for computation. In the DSMC algorithm, we constructed the dominance graph from the inner product Dionis graph, which is a directed graph to represent the loss of removing an extreme point and using another point to represent it. Such a loss for each pair of points can be computed by a linear program, and all pairs of points with positive losses correspond to the edges in the directed graph, with the losses as edge weights. For solution computation in DSMC, we first get a subgraph containing edges with weights at most epsilon. Then we find a dominating set of the subgraph using the greedy algorithm as the solution for MC. Here are the theoretical results of the DSMC algorithm. Next, I will introduce the SCMC algorithm, which is a variant of the set cover or heavy set-based algorithm for IMS in existing works. The basic idea is to discretize the sphere based on the notion of data net, and the difference from the algorithms for IMS problem is that we should sample the data net from the whole sphere instead of only the positive ascent of the sphere. Here I will introduce the main steps of the SCMC algorithm. The first step is to sample an alpha epsilon over 4D net of the sphere. Then we will construct a set system between the points in P and the vectors in the net. Finally, we will compute the smallest set, the minimum set cover of the set system as the solution for the MC problem. Here are the theoretical results for the SCMC algorithm. Here are the algorithms we compare in the experiments. Except for our proposed algorithm, we also use the standard approximate nearest neighbor based algorithm for epsilon kernel computation for comparison. Our C++ implementation of all algorithms is published on GitHub. We use several publicly available real-world datasets as well as synthetic datasets in our experiments. We evaluate both the efficiency and solution quality of the algorithms we compare. In the experiments on two-dimensional datasets, the optimal algorithm always has the best solution quality but runs the slowest. DSMC and SCMC run much faster than the optimal algorithm and can provide near-optimal solutions. The sizes of the solutions returned by the ANN algorithm are significantly larger than other algorithms. In the experiments on multidimensional datasets, DSMC achieves both better solution quality and higher running efficiency, especially when the value of epsilon is smaller. The SCMC algorithm runs slower than the DSMC algorithm, but can also provide solutions of higher quality than the ANN algorithm. That's all for my presentation. Thank you.